In this last video of this lecture, I want to introduce some concepts that'll be a focus for the next lecture. That is, what it means to be an algebraic closure of a field F, and what it means for a field to be algebraically closed. So what's the idea? If f of x in f bracket x is a polynomial, the splitting field for this polynomial over f is an extension of f that contains all of the roots of f of x. So what if you want an extension that simultaneously is a splitting field for many different polynomials? Well, you can do that by taking the composite of some splitting fields, say if you have like 2 splitting fields or something like that. But what if you want to be a splitting field for every polynomial in f bracket x at the same time? That is there an extension of f that simultaneously contains all the roots of every polynomial in f bracket x? Every polynomial in f bracket x, we want to factor completely in a product of linear factors in this big extension. And the answer is yes. All right, so the definition that I want to give now is that the field f bar is an algebraic closure of f if every polynomial in f bracket x splits completely over f bar. What would that mean? What are the elements that are algebraic over f are exactly the elements that are roots of polynomials with coefficients in f. So that means that such a field, this algebraic closure, has to contain every element that is algebraic over f. So this notation is not completely new. In the last lecture, we let q bar be the subfield of C containing every element that is algebraic over q. Why do we use this bar notation for both? Because this is an algebraic closure of q. We'll come back and talk more about this later, but I just want to point out that using this notation for both makes sense because this is one instance of this property of being an algebraic closure. All right, so we know algebraic closure. What about algebraically closed? A field K is called algebraically closed if every polynomial with coefficients in K has a root in K. All right, so this is only an interesting thing to define if there really are examples of fields with this property. And later on, we'll see that the complex numbers is a field that is algebraically closed, that the complex numbers really does have this property. But we'll see this a little later. So what do I want to address right now? What I want to address right now is there's a bit of a bait and switch in this definition, right? Because algebraic closure of f means that every polynomial in f bracket x splits completely over f bar. But algebraically closed, all we're requiring is that every polynomial in k bracket x has one root in k. We're not saying that it necessarily splits completely in k bracket x, but it does. So we'll see that this is a standard definition of algebraically closed to give, but in fact, it is equivalent to the one where you would be asking for something that looks a little bit stronger, where every polynomial in k bracket x splits completely in k bracket x. So I'll explain that, and then I'll state a big result that we're going to prove in the next lecture. Let's think about this definition of what it means for k to be algebraically closed. Every polynomial in k bracket x has a root in k. So we can show that if k is algebraically closed and f of x is in k bracket x, then not only is there one root of f of x in k, but every root of f of x is in k. So this definition is equivalent to this stronger one you could imagine requiring where you want your polynomial to split completely into a product of linear polynomials in k bracket x. These are the same. And how do we see that? The idea is induction on the degree. So we know that there's one root alpha of f of x in k. So how does f of x factor? It's x minus alpha times g of x in k bracket x, because having a root is the same as having this linear factor. So now let's look at g of x. G of x is a polynomial with coefficients in k, so it also has a root in k. So g of x has a linear factor. So we can pull that one out. and do it again and again and again and again until there's no more linear factors to take out. So that's the idea. So in fact, every root of f of x is already in K. Okay, so what are we seeing? We're seeing that if K is algebraically closed, then K is an algebraic closure of K. That every polynomial in K bracket x splits completely in K. And the converse is clear that if K is an algebraic closure of K, then K is algebraically closed. Just look at the definitions and see what is being required. So what does that mean? That means that K is equal to an algebraic closure of K if and only if K is algebraically closed. Okay, so this is a basic property that is good to know. The big thing that we're going to prove in the next lecture involving algebraic closures is that algebraic closures exist. This is not at all clear that such a field exists. We're going to prove proposition 30 in section 13.4, which says that for any field f, there is an algebraically closed field K containing f, that there is an extension of f that is algebraically closed. So we will prove that next time.